Welcome, everyone, to the March 2023 Martin Gardner Celebration of Mind Talk. I'm Bob Hearn. I'm your host. I'm the Gathering for Gardner program chair, and I'm very pleased today to be able to introduce Kate Stange, who is a number theorist and a cryptographer from the University of Colorado at Boulder. And I'm very much looking forward to this talk. It's got lots of beautiful and interesting mathematics in it.
All right, so thank you very much for the invitation to be here. And yeah, it's a fantastic honor to be here with G4G. So since I was a kid, I was always really fascinated with all of the amazing things that evolution has come up with, all of the variety of nature, the crazy things that animals can do. There's a fungus which can invade the brain of an ant and actually control the ant's brain to make it walk exactly 25 centimeters above the ground so that it can then spread its fungal spores from the optimal height. My son is really into lizards, and so he taught me that this adorable little lizard right here, if he feels threatened, can raise the blood pressure in his head and shoot blood 5 feet out of his eyeballs. And then there's rain frogs, which they're just amazing just by their very existence. And so as I've become a mathematician and a number theorist, I feel like my experience is a lot the same. I like to wander around and sort of see what the mathematical objects are doing. And I like particularly that now we live in this modern world where we have computer tools. We can really illustrate what's happening with computer illustration, computer visualizations, experiments. And sometimes we can see more behavior than maybe we realized was there. And so today I want to sort of revisit some of these familiar objects. I'm going to be talking about things like polynomials, the roots of polynomials, but hopefully from a new perspective, hopefully from a visual perspective, and something that people maybe haven't seen before. Okay, so I want to start with a simple experiment. So I want to look at the roots of polynomials. I'm a number theorist, so I want polynomials with integer coefficients. If I let the coefficients vary continuously, then the roots will sort of vary continuously. But if I choose integer coefficients, then maybe some interesting discreteness will be happening here. I'm going to limit myself to quadratic polynomials because that's a nice simple place to start. So we have 3 coefficients, A, B, and C, and I'm letting those be integers. And I just want to know, what do the roots look like? So we know the quadratic formula will give us the roots of that equation. And so here's an example, x squared minus 1. So that has roots 1 and minus 1, and we could put them on the number line. But then, of course, we have x squared plus 1, which doesn't have real roots. It has complex roots. And so we invent the imaginary number I, which should square to minus 1. And that's not on the real number line. So if we want to draw it, we're going to put it, somewhere else in the plane. And it's really just a conventional choice to stick it, nice and symmetrically up there above 0. And so now this polynomial will have roots at at I and minus I. And now I have the whole plane to work with to look for other roots as well. So for example, 1 plus I now is at these new coordinates in the plane. So I could take some other polynomials. I could do this one, which has some simple coordinates, and there are its roots in the complex plane using the quadratic formula. Here's another one. And I could keep doing this. And if I keep doing this, I'm going to eventually just fill up the plane and it'll just be completely black with dots. And so maybe I haven't learned anything from that. But if I think about how to draw the picture with a little bit more nuance, one thing I could do is I could decide to make some of the dots more important or more fundamental than others. I mean, the polynomial x squared plus 1 is one of the first ones in some sense, one of the simplest ones from this infinite collection of polynomials. And so I might make those dots larger, and then some of the maybe more complicated polynomials, I could leave their dots smaller. So if I sort of size the dots by complexity, then there's some hope to see some structure in this, because maybe the more complicated ones that we get to much later when A, B, and C are very big will sort of fade into the background. So what I'm going to size by is the discriminant, which is the number under the root sign in the quadratic formula. All right, and this is what you get. And so the real line is along the bottom of the screen. So I don't know if you can see my mouse, but this is 0 down here and 1 and minus 1. And then this is the imaginary axis heading up the middle, and this is I. So I haven't actually drawn the real roots because they're much too crowded. So I'm just drawing the upper half plane in the complex plane. And you immediately see there's a lot of structure here. There's some sort of periodicity. There's also like this sort of beaded necklace effect. There's almost a 3D effect. There's lots going on. And you wonder, okay, so what's the explanation for all of the structure? What's going on in the picture? So that's what I want to start with. Okay, we have to back up though. And I'm going to back up all the way to the rational numbers, which is really in some sense looking at linear polynomials instead of quadratic ones. And I want to ask again, you know, how should we really think about a rational number? And then we'll eventually build back up to the quadratics. Okay, so what's a rational number? So here's an example rational number. Maybe it's a pair of integers, but of course it's not really quite the right answer because 4/6 is the same as 2/3. So it's really about the ratio, right? And one way of capturing a ratio between two things is as a slope. So we could imagine the rational number 2/3, you know, take 2 and 3 as the rise over the run and make a slope. Then 4/6 is the same slope, but maybe you imagine it sort of going further because you're going all the way to the point 4/6. So the way I want to visualize a rational number for the moment is to think of it just as you're standing at the origin and you're looking out at the lattice of integer coordinates in the plane. So in red here are all the coordinates in the Cartesian plane that have integer coefficients, integer entries. And I'm looking out from the origin. And if I look at the point 2, 3, I'm looking out along this ray that I've highlighted in blue. And that's what I want to think of as the sort of visual representation of the rational number 2/3. So here's some other examples of rational numbers. You're standing at the origin and you're looking out at this lattice, and what you kind of see as you look around is the collection of rational numbers. And so now, hopefully the video is working okay. I'm above this lattice that we've just been looking at, and I'm now going to zoom in. I'm going to zoom down to the origin, which I've made a bigger ball right there. And I just want you to watch the visual effect of the lattice points under perspective. And think of them as the rational numbers that you're looking out at from the origin. And I'm actually going to enter that ball. That's what's happening right now. So now I'm inside the origin looking out. And I'm looking at the rational numbers. And now that I'm down into the plane of the lattice, I'm actually looking out. It's as if I'm looking at the real line. And those are the rational numbers sitting in the real line. All right. So what I want to do is organize the rational numbers according to this system I've just described, okay? So 0 would be out along the x-axis down here, and 1 would be heading out this direction, and you're seeing this ball denoting 1, and you're seeing sort of a ball right here at 1, comma 0 denoting the point 0. Now, I've kind of done a mirror flip thing, for which I apologize. I should have maybe designed this better. They're on opposite sides here. But imagine I'm standing at the origin, I'm looking out, and I sort of see these two big balls, the two nearest points in the lattice. And I can kind of think of that as my fundamental interval. And I'm just going to sort of draw an arc above to sort of indicate that that's my fundamental interval. And then if I want to know sort of, okay, those are the most fundamental, most simple rational numbers. What's the next most complex rational number? Well, it would make sense to sort of take the next biggest ball in my field of view, which is this position over here out at 1/2. And in the lattice, it's actually just the lattice sum of those first two vectors. If you write it as fractions, it looks a little bizarre. It's the mediant operation where you're adding the two numerators and adding the two denominators to get a new numerator and denominator. So this mediant operation, of course, doesn't really correspond to something that we're familiar with rational numbers. It's not just addition or something, but it is kind of the way of making the next most complicated rational number between the two that you have. And so from this interval, I'm going to subdivide into these two smaller intervals like this. And then I can keep going. So in between 0 and 1/2, we get 1/3 as sort of the next most prominent ball, then 2/3 on the other side. And I can keep subdividing, and each time it's a sort of lattice sum in the lattice. Okay. And this is, I claim, the most natural way of organizing the rational numbers. So here's an illustration of this process going a little bit farther. So we just keep subdividing these intervals, and we keep generating the rational numbers, and we kind of generate them from the simplest ones to the most complex ones as we go. Okay, and now, like I said, I claim that this is sort of the most natural and best way to organize the rational numbers inside the real line. But, you know, it's just one choice. compare it to the decimal subdivision, which is how we usually organize them. We just break it into 10 pieces, and then within those 10 pieces, we say, what's the next choice out of 10 sub pieces of that? But of course, this is, well, it's less beautiful, right? And I think there's one of my sort of theses is that if you follow the beauty, sometimes that leads you to the best mathematics. And so there is something about this so-called Farey subdivision, which is really very natural and amazing. Okay, now I was going back to it there. All right. Okay, so I just want you to get this visual fixed in your head before we go back to the quadratic case now. So just see the shape that the rational numbers take. This is where I should have some carefully chosen music. Okay. So now this visual effect that we're seeing right here should be reminiscent of what we were seeing in the quadratic picture. So let's go back to that. We're sort of seeing, it's as if we have these sort of necklaces, this view from the origin of the rational numbers, but all over the complex plane now in curves. So what's happening? I mean, there is a sort of three-dimensional or maybe even higher dimensional kind of effect to this. So you might wonder if it's sort of a higher dimensional version of something similar happening. Maybe there's a lattice hiding in this problem as well. And so the natural place to look for a lattice is those coefficients which I've chosen, right? So I was looking at the roots of polynomials where a, b, and c were integer coefficients. So if we look in the coefficient space, a, b, and c are the integer lattice in the space with 3 dimensions for a, b, and c. Then the lattice looks something like this. I mean, of course, it continues out to infinity. And remember that I sized the dots according to the discriminant. So what is the discriminant? Well, the discriminant looks like b squared minus 4ac in terms of these variables here. And we could draw that locus. So we could say, where is b squared equal to 4ac? Where's the discriminant actually 0? And it turns out that that's a double cone if I were to draw that into this space. And so, as you may know, the discriminant, whether it's positive or negative, determines whether we're talking about complex roots to this polynomial or roots which lie in the real line. And this is the dividing space between those two phenomena. So outside the double cone, in the space in between, we have polynomials which have real roots. And inside the ends of the cone, we have complex roots. Okay. Now, if I were to pick a different value for the discriminant, say the discriminant should be -1, that would give me a sort of level set here. This is a double hyperboloid fitting inside the cone. And as the discriminant gets larger and larger negative, I'll just nest these sorts of hyperboloids in this space. Okay, so now let's actually visualize with the computer. So here's my 3-dimensional lattice. And first, I just want to sort of watch the visual features that you see as you watch it kind of rotate in space. And then I want to add in that discriminant cone in a moment. There's my discriminant cone. So right now we're outside and we're seeing the points which correspond to polynomials that have real roots. And now as we rotate, we're going to look inside one of the cones. And these are polynomials which have complex roots. And what I've done is I've added just a membrane across the cone. It's just sort of a landing pad. So what I want to do is I'm going to look straight down. I'm going to pull in all of the lattice points towards the origin until they hit this kind of canvas, and they're going to stop when they hit the canvas. So it's a way of capturing all those points, but in a 2-dimensional canvas. And if they were near the canvas, they are large, but if they were far away, they shrink as they head in and they end up small on the canvas. All right. So in this picture here, we're sort of looking at all of the polynomials, all the positions in the space of coefficients, which correspond to polynomials with complex roots. And they're sort of sized according to their complexity in the sense that if you remember, as you're like further inside the cone, you have a larger negative discriminant. And if you're sort of near the edges of the cone, sort of not going to take you too long to hit this membrane, you have a lower negative discriminant. So they're sized a little bit like what we had in our picture. And we see some of the same shapes going on now. We've got these sort of beaded necklaces going in all the different directions. But it's not exactly the picture we had. The picture we had was the actual roots. This is the coefficient space. So how do we get from the coefficient space to the root space? There's the root space. This is how it happens. We take that oval canvas and we open up the oval to become the real line. It was actually, yeah. Okay. And so that's actually taking you from the coefficient space to the root space, which means this is actually the quadratic formula. So this is geometrically what's happening when you apply the quadratic formula. And then I also preserve the size according to the discriminant to give the picture a bit more structure. So so this all came about while we were at ICERM, which is the Institute for Computational and Experimental Research in Mathematics in Providence, Rhode Island. And we were there. I was one of the co-organizers of a special semester on illustrating mathematics. And we just got interested in this experiment that I just shared with you. I mean, we were just drawing the roots of polynomials and trying to kind of understand the picture. I was working with Steve Treadle and Edmund Harris, whom you see here. And here are some other pictures from that semester. It was a very exciting semester. You can see my son, you can see my co-organizers. Maybe you can't tell the difference. And it was a very exciting place to be. People were doing all kinds of amazing things there. And we noticed, we discovered what I just said about the quadratic formula having this geometric interpretation. And we've looked, and this is a question perhaps for the audience, we haven't actually seen that description anywhere else. I'm sure it's not new. Quadratic formula has been around for ages, but we haven't come across or been able to find any description of it in the same geometric way. All right, so we got interested and we said, what happens if you take higher degree polynomials? So this became a bit of a research project, and we looked at cubic polynomials. So these are the roots of cubic polynomials with integer coefficients. These pictures, by the way, are done in Mathematica by Edmund Harris, who's also, he has actually a cross appointment between mathematics and art at his university. And so what we did is we basically took the coefficients in a box out to a certain distance, right? Because there's infinitely many such things, but we drew finitely many in some box around the origin of the coefficient space. And so you can see some amazing stuff here. One thing you can see is the way that it kind of avoids the space that was occupied by the quadratics. But you can also see that it's incredibly complicated. I didn't know what would come out the best in Zoom, so there's a few sort of different flavors here in terms of the colors. Here's a close-up of it. And we called these algebraic starscapes because they definitely look like something astronomical. I mean, I don't know if that's a supernova or a galaxy or some planets or what, but there's definitely that feel to it. And you'll notice that there's definitely these sort of beaded chains again. So it's as if the same phenomena is going on, but so there's just like a riot of things. There's not, you can't see the structure because there's too much. And if you think about what might be happening, we have a higher dimensional space of possible coefficients that we're trying to smoosh down into the complex plane. And so maybe it's just like we're dropping too many dimensions, right? So here's if we take some families of cubic polynomials. So if we take the x squared and x coefficient to be the same, for example, then you start to recover some of the same beautiful structure that we had from the quadratic case, but much more interesting variety is happening. So this one is actually showing the quadratics in black and the cubics in red. And here's a few other sort of choices of families. And these are all laying on top of each other in that original picture, but we're just isolating sort of one family at a time, three-dimensional families. This one's amazing. There's so much going on. That's right at I in the complex plane. And here's one where we've fixed one of the coefficients to be 3. So we're taking a family, but it's not like a hyperplane through the origin. It's not passing through the origin. And so you start to see some of this, rotational behavior that we picked up in the first picture. And here's one where it's I've taken a 2-dimensional family. So this only has an A and a B in the choice of coefficients. And you can see now how similar that looks to when we were flying down into the lattice. This is a 2-dimensional lattice, which is in some interesting way been embedded into the complex plane by some kind of geometry. And so a similar kind of thing happens. You can take the discriminant for the cubic polynomial. Now it's in a high dimensional space, and so this is a sort of projectivized representation here, but just to give a vague idea, there's a locus where you have a triple root to your polynomial, which is lower dimensional. That's on the left there. And then there's a double root locus, which is sort of a membrane which separates the case where you have 3 real roots from the case where you have 1 real and 2 complex roots. So it's similar to the case for quadratics, but has a few more things happening. And if you take the coefficient space and you choose to highlight this discriminant locus and break it into pieces like this, then you can describe the geometry of how each of these pieces maps into the root space. So if we want to map into the complex plane, we're really looking at the one on the right here. We're interested when there's 2 complex conjugate roots, and we're going to take the one in the upper half plane. So something similar kind of happens. One way to think about what's going on is to take your cubic polynomial, like I have at the top of the screen here, and we're interested in the case where it has 2 complex roots. So we'll call those Z and Z bar, complex conjugate roots. Here's my real root, and then I have a leading coefficient. So the real root is a one-dimensional thing. So think of that as the dimension going along, like this is a long tube. And then inside each slice, so you fix the real root, you're now in the quadratic case with 2 complex conjugate roots. And so if you slice off a little piece of this long tube, you end up with a little copy of sort of the quadratic starscape. And then just like we did in the quadratic geometry, we can kind of open up that bounding circle and make it into the real line to see it sitting inside the upper half plane. And so this is a 3D visualization, a sort of fly through of this tube where I've connected the ends. So it's actually a bagel because it's very natural to connect minus infinity to infinity. And so the slices, like bagel chips here, are sort of copies of something that will look like the quadratic case, but the whole thing is the whole space of cubics where you have 2 complex conjugate roots. And this is software due to David Dumas, who he was interested in visualizing point clouds in some other context. His context also involved a torus. And so we were able to just use the software that he had made already, which is fantastic. We have a website where you can visit these things. You can play with his software. And so this is just me playing with it on the computer. You can rotate it with your mouse and sort of see some of what's happening. And so now you can see how much structure there is, but that picture of just one copy of the complex plane that I showed at the beginning is if you smoosh the whole torus down along the circle which travels around the torus, like perpendicular to those bagel chips, you smoosh all those bagel chips into one, and then you kind of lose your ability to see all of this intricate structure. Okay, all right. So that was just the beginning of an exploration, which could go much further. I think it'd be kind of interesting to take it beyond cubics, but it was already quite a challenge to figure out all of the geometry of the cubic integers. But this is actually related to something in number theory. And so now I want to switch gears a little bit and tell you about something related, but in a different direction. And we'll come back to connect it to the starscapes. So the question that I want to ask you, and I'm sure this is perhaps a question which has come up in G4G talks before maybe, is this question of approximating some real number with rational numbers. So it was Pi Day recently, and 22/7 is this very famous rational approximation to pi. And the idea is that if you pick a number with a small denominator like 7, you should really only expect to be able to approximate your number of choice to within like a 7th or maybe a 14th or something, right? And yet pi is approximated by 22/7 to within 1/790th, which is much more than you would expect sort of for the price of the denominator. It's as if you're shopping for good approximations and you want to get a cheap one where you pay for the denominator, but you want a good one that's very close. And so a good approximation is one that's cheap for its quality. All right. So this is a long-standing question under the name of Diophantine approximation in number theory. And here's a picture of or visualization of approximating pi. So here, if you imagine putting pi into the real numbers, it's as if you're choosing a slope of angle pi in that first visualization that I had. And so from the origin, you can kind of travel out along that line of slope pi, and you see the rational numbers, which are fairly near the line. And those are the good approximations. So 19/6 is, you know, it's okay. But look at 22/7. It's like so dead on, you can't even tell that it's not perfect in this visualization. And so that's kind of the what we're looking for when we do Diophantine approximation. Here's another way of visualizing it, going back to our visualization of the rational numbers. In this Farey subdivision, you sort of imagine this Farey subdivision as giving structure to your real line, and your number that you're interested in, you pick it somewhere in the real line in here, and you want to know which rational numbers, which big balls are going to be near as you sort of fly through the lattice. And another way of thinking about that is to say, use the Farey structure as a sort of addressing system, as kind of driving directions to get to your number. So you could imagine that you're outside and you want to this interval here, and then you want to know, do I go to the left or to the right to get closer to my number of choice, pi or whatever it is? Well, in this example here, I choose the right bubble to enter, and then I have two sub bubbles inside that, and I'm going to choose one of those to go into, and so on and so forth. And so I can explain what the number is by giving sort of driving directions. And this is very similar to what we do when we have a decimal expansion of a number. You know, the first decimal says, you know, which of the 10 subintervals do you go into? And then the next one is the 10 subintervals of that. So this is the same idea. And this geometric description is due to Carolyn's series. And what she realized is that this is actually the geometric description, the easiest and I think most beautiful geometric description of continued fractions. So if you happen to be familiar with continued fractions as a way of expressing a number in the real line, this is actually what the continued fraction expansion is telling you. Just in the same way that a decimal expansion is giving you driving directions through the decimal subdivision, the continued fraction expansion driving directions are how many lefts do you make? How many rights do you make? How many lefts do you make? Those are the numbers in the expansion. What we might ask is, we might say, what if we wanted to approximate complex numbers? So we can't approximate them by rationals because the rationals are all stuck in the real line. They're not going to do very well. So here's the upper half plane again. So this is the complex plane. Just to remind you, the real line is down at the bottom down here, and this is the imaginary axis. And I might ask, okay, well, these quadratic roots, they fill the complex plane in kind of a similar way to the way the rationals fill the real line. And so maybe I could ask about approximating complex numbers with quadratics. So I could pick some complex number in here and ask for what are the best approximations, what are the quadratics which are closest, but for the price of maybe the discriminant or some other measure of complexity. And so this is a question people have asked for a long time. Usually the measure of complexity is something like maybe the maximum of the coefficients. It's not usually just the discriminant. So there's various different ways that would correspond to essentially to sizing these integers a little bit, sizing the dots a little bit differently. But the discriminant gives you this beautiful periodic one. And so in some sense, it's the most natural visually, I think, after experimenting with the various sizes. And a lot of them are sort of equivalent to one another, especially if you kind of restrict yourself to a little piece of the complex plane. Okay, so let's use the discriminant, and we'll say, I want to approximate some number here with quadratics, which are not too complicated, but approximated well. And there's a result of Bouguer and Averze that describes some of the complex numbers as being sort of fundamentally more approximable than others. They have many more better approximations than others. And imagine these blue dots here are points in the complex plane that you want to approximate. I'll tell you what they are in a second. If your blue dot lies on one of these one of these lines, these beaded lines in the picture, then you're going to have a lot of good approximations because you have so many things already in that same line that are approaching you, kind of the way you have rational approximations when you're in the real line. But if you pick a dot which is sort of off one of these lines, then you have a harder time because to approximate it, you have to first have a near flyby of one of those lines and then pick something on one of those lines, right? I mean, the lines fill in densely, but if you're trying to get good approximations, you're looking for these, you know, the simpler ones. And so if you're kind of off those lines, you're always going to be pulling your approximations just from nearby lines instead of the thing that you're sitting on. And so there's these two fundamental phenomena that are different. Bujold and Averza realized this, but in a completely algebraic way. And when we drew these pictures, it became clear what the geometric meaning of their algebraic condition was. It's you're on one of these lines or not. And so the picture tells you about approximability and a lot more, the sort of new phenomena that's not happening in the real line. So in case you were curious what the blue dots are in this picture, this is, these are, if I remember correctly, these are quartics plotted, and then we're trying to approximate them by quadratics. So roots of polynomials of degree 4 are the blue dots. And so now I want to switch slightly, but again, related to the same question of approximation. I want to switch to another way to think about approximation in the complex plane. Okay, so remember we had the Farey subdivision, which is if you want to approximate your point, you can kind of give driving directions to it. And as you go down through those bubbles, here, let me go back to the picture for 1 second here. As you go down to this point right here, the good approximations are these turning points. So I'm turning around this point here. When I cross this line, I'm sort of turning around this point. And then as I cross this, I'm turning around this point. So these like corners in the description as you go down are going to end up being the good approximations. And so we might try to do something like that for the complex plane. But in the complex plane, we would need something kind of like the Farey subdivision. So let's say we wanted, so the problem that I want to focus on would be, let's say we wanted to approximate a complex number, not just by any quadratics, but by Gaussian rationals. So that means that I want to pick points in the complex plane that are of the form a rational number plus a rational multiple of I. Okay, those are called the Gaussian rationals. And here's a picture of them, again, sort of sized by complexity. So they have a lot of beautiful structure, just like the rationals do, but it's a little different. It's a new, different sort of pattern of these things. And I want to approximate some point in the complex plane. So I want to find large dots, which are near it, which are very close to it, but are still big dots. Okay, so as Ms. Schmidt thought about this problem, and this was before personal computers were common. So he has these beautiful drawings of a way of breaking up the complex plane into pieces, kind of the way the subdivision breaks the real line up into pieces in that sort of bubbly froth. And what he wanted to do was break it up with these domes, like circles, and the triangles that ended up between them. And so here's his picture, but he never drew it on the computer to see what it would look like if you kept iterating it the way you do the Farey subdivision. And so if you do that, here's the picture. So here's the successive ways of breaking up the complex plane into pieces, which is somehow analogous to the Farey subdivision. And we're just adding more and more of these as we go. Now, there's one of these notions of a subdivision like this for the Gaussian rationals, but you might try to approximate by roots from other quadratic fields if you're familiar with the terminology. Okay, and so you get this incredibly intricate. There's also on my screen behind me, if you can, I don't know if you can see my picture at the same time. This incredibly intricate nested circles. They never cross, but they can be tangent. So they're either tangent or completely disjoint, and they just fill the plane completely. So for orientation in the plane here, this where my mouse is now is 0. This is 1, and up here above 0 is I, the imaginary I. This is 1 plus I over 2 in the darker color here. Okay, here's another picture. This one, I've thought of each circle as a dome and made them transparent so you can see which ones are nested inside which ones. And I made a 3D model of these so you can actually see them as domes. And if you look from above and just inside one dome, you see what's called an Apollonian circle packing. If you look from below, you can see all of those nested domes, just like in the picture we were looking at a second ago. And so you can actually use these to approximate a complex number. So for example, if I have, if I choose some point, like hopefully you can see my mouse choosing some little point in here, then I just, as its sort of address in the complex plane, I say, okay, so you go outside the big first circle, and then you go into the triangle, which is to the upper right, and then you go to the triangle that, you know, break that into pieces by putting a circle in the middle, and you go into this triangle over here, and then you break that into pieces, and so on and so forth. And that is a sort of notion of continued fraction expansion for complex numbers. And this is all due to Asmus Schmidt. He studied other number fields as well, so I'll just show you some of the other variations on it, depending on what you want to approximate by. And they all have their own character. As a number theorist, I study number fields, these number rings that involve, you know, the square root of something that doesn't exist in the integers. And each of these has its own personality. You can see a different kind of symmetry in each of these, and you can learn a little something about the number theory from these. So for example, this one is actually disconnected. It has these sort of like ghostly circles that aren't drawn here, kind of breaking up the plane into pieces, whereas some of them are connected, and that's reflected in the number theory. So I'll just show you a few more of these images. And as I said, Schmidt studied a number of these, and then I kept drawing these on the computer and drawing more of them. And one of my research projects was just to take a look at what is the relationship between the geometry and the number theory. What things can you say about the number theory from studying these pictures? And this is one of my absolute favorites. I love this one. And yeah, I'll end there with a web link and also some information about the different software and things that I used for making all of the images and stuff in the talk. So thank you very much.
Wow. Thank you, Kate. That was absolutely wonderful. And you probably were not watching the chat, but you know, comments along the lines of beautiful. That was cool. Wow. I've been waiting for someone to blow my mind. This is amazing.
Oh, I should have been watching the chat.
Yeah.
Thank you.
So that
yeah,
is
it went a little faster because usually I'm answering questions from the audience and stuff.
Okay. Yeah. Yeah. Well, fortunately, that does leave us with time for some questions.
Yep.
So my question is there something interesting about the the complex plane continued fraction approximations of, say, the roots of the Riemann function on the you know, at a half or something like that?
Wow, I don't know. I've never thought about that question. That sounds fascinating. Yeah, I mean, so the theory of continued fractions and rational approximations, Diophantine approximation, is a long, you know, it's a very old theory with a lot of history, but a lot of it is done in the real line, approximating by rationals, because it's the most obvious first case. And there are a lot of really interesting, like special values of special functions and stuff like that have interesting continued fraction expansions, work of Ramanujan and stuff. You can find fascinating stuff. So maybe, I have no idea. That's a fascinating question.
So Susan Goldstein asks, does the disconnectedness relate to the non-uniqueness of factorizations?
Yes, absolutely. So it's actually whether or not the ring of integers is Euclidean. So I can say a little something about that for those who are familiar with the terminology, at least. So we have, like, here's a connected one where you can get from the real line to anywhere, and here's one where you don't. So down in the bottom right of the screen, I've written PSL2 of a ring of integers. So what this is the Mobius transformations. PSL2 of the complex numbers represents Mobius transformations as matrices. So to draw the picture, what you can do is you can take the real line and you apply all of the various Mobius transformations in your chosen collection which is what I'm denoting at the bottom of the screen there. And each of the images of the real line will be some circle somewhere. And the structure of that matrix group, it turns out that when you have a Euclidean number field, the matrix group is generated by elementary matrices, which the elementary matrices are kind of like the steps in the Euclidean algorithm somehow. And so you can get anywhere with those matrices. And when you have a non-Euclidean situation, then you can't get anywhere by the elementary matrices. And so you have these sort of disconnected components because the elementary matrices kind of travel by tangencies. And so you have to, tangencies won't get you everywhere in this picture. So that's very brief, but yeah, that was one of the things that was a result of that research project, which was really fun to see visually. It's a totally different visual interpretation of the Euclideanity of the field.
Great, thank you. Next question. The size of the dots was related to the size of the discriminant. Is the radius of the circle proportional to the size of the discriminant?
So we use 1 over the discriminant to some power, and we sort of optimize that power for the pictures to look good. And so we found, I can't remember now exactly what we picked for the ones we were looking at, but it might have been 1 over the discriminant squared, so that as the discriminant grows, the radius shrinks.
Great. Dan,
you can find out exactly what it is in the paper.
Well, did Kate answer the question about factorization?
Oh, I didn't actually use the word factorization when I answered that question, which is, so if you have the ring of integers of a quadratic imaginary field, the question of factorization is not exactly the same as the question of being Euclidean. But if you're Euclidean, then you have unique factorization. But there, as the size of the discriminant grows, you lose unique factorization, and these pictures tend to get more and more disconnected. But what you actually capture is the Euclideanity, not the factorization, not exactly the same thing.
Thank you again. That was beautiful, insightful. I'm definitely going to have to go back and rewatch and appreciate the transformations again. Thank you again, Kate.
Thank you.